Today we're going to talk about finding derivatives of exponential and logarithm functions. There's a couple of things that we'll have to do and kind of maybe not really take for granted, but I'm gonna let you work with the calculator on these things and determine that what I'm actually telling you with this stuff is true using our table formula like we've talked about as far as finding limits in the past, especially when it comes to the exponential functions. But let's start off with finding the derivative of an exponential function in general, and we're going to be talking about using the function y equals a to the x. I'm going to do this a little bit more specifically when it comes to this, just because it gets a little bit easier to do when we're talking about exponential functions to actually choose a value for a. So in my process that I'm going to start off with here, I'm actually going to start with looking at the function y equals 2 to the x. The 2 there, the base that we're using for the exponential function, really can be anything. It doesn't really matter what that function is or what that constant is. The process here is going to be the same. We don't do a lot with bases other than e in this class. You will see it occasionally, but what I'm going to do is I'm going to do this with a constant of 2. We're going to generalize that and show that it's actually what the derivative is for any constant there. And then we're going to talk primarily about how to take the derivative when you've got something like e to the x, which actually makes things a little bit easier to do as well. So we're going to have to go back to our limit definition of derivative with this problem. So if you remember, our limit definition said that when we take the derivative, we have to take the limit as h goes to 0 of the original function evaluated at x plus h, so in this case that's going to be 2 to the x plus h, minus the original function, which is 2 to the x, and that's all divided by h. So we can't just plug in 0 here for the same reason that we haven't been able to before. We've got an 8, we've got 0 in the denominator if we do that. So we're going to have to do some algebraic simplification with this thing. And when we do this, the first thing that we're going to do, there's no factoring or anything that can occur right now with what we have. What I'm going to do though is I'm going to take this, I'm going to say that's the limit as h goes to 0 of 2 to the x times 2 to the h. Remember that when we have two functions that are being multiplied together with the same base, we can add the exponent. So 2 to the x times 2 to the h is the same as 2 to the x plus h. So I have 2 to the x times 2 to the h minus 2 to the x, all divided by h. And what that's going to allow me to do is, now in this numerator, both of these terms in the numerator have a 2 to the x. So I'm going to factor that out. And when I do that, I'm going to get the limit as h approaches 0 of 2 to the x times 2 to the h minus 1, all divided by h. And notice here that now that I've got this 2 to the x out front, the 2 to the x is not being affected by this limit at all. There's no h involved there. So I'm actually going to take that 2 to the x, I'm going to slide it out to the front here. So this is going to be equal to 2 to the x times the limit as h goes to 0 of 2 to the h minus 1, all divided by h. And this is where I'm going to leave this to you to actually evaluate this using your calculator. Plug 2 to the h minus 1 over h into your calculator. You'll probably want to use an x there so that you don't so that your calculator can evaluate this. And then use your table to find what the limit as h tends to 0 is. Now, it's going to give you a really strange number, but one that you're probably not going to recognize. What I want you to do, once you find what that limit is, once you see what's happening as h approaches 0 from both sides, it should be, I think it's like 0.69, somewhere around there. And what I want to tell you is that that limit actually evaluates to the natural log of 2. Okay, so if you find out what this limit is and find the numerical value for that, and then go back to your home screen and evaluate the natural log of 2, you'll find that that's actually what this limit is. And what's happening here is, regardless of what this base is, if this was 3 to the x, then this would become 3 to the x times the natural log of 3. If this was 6 to the x, then this would be 6 to the x times the natural log of 6. So whatever that base is right here, we're always going to have, and we can generalize this now, for any exponential function, the derivative of that exponential function is going to be a to the x times whatever the natural log of a is, whatever the natural log of that base is. So that's the way that this proof is relatively simple to do, other than actually evaluating this limit, which we don't have an algebraic way to do. We have to do that using our table of values from our calculator. But this is the general formula that we'll use. Now, what I want to note here, like I said, we use e to the x quite a bit. That's the one that you're going to see most often here. So if our function is y equals e to the x, then according to my derivative rule here, then the derivative of that is going to be that y prime is equal to e to the x times the natural log of e. But the thing that's interesting about that is that the natural log of e is actually equal to 1. And so this actually just turns out to be e to the x times 1, or just e to the x. So the derivative of e to the x is e to the x. It's one of the few derivatives that we have, or a few functions that we have, that actually serves as its own derivative. So that's kind of handy. We like those e to the x functions. They're really easy to differentiate. If you've got the derivative of e to the x, the answer is e to the x. Now, that becomes a little bit more complicated when we start using some chain rule issues and product rule issues involved in that. So let's take a look at a couple of problems to see how that would be, how we would resolve that. So let's say that we had the function, y equals the cosine of x times e to the x. Cosine of x times e to the x. So we've got two functions that are being multiplied together here. That tells me right away that I have to use the product rule to differentiate this. And the product rule tells me that I have, let's see, y prime is going to be the derivative of the first function. The derivative of this cosine function is negative sine. So I have negative sine of x times the second function, which is e to the x, plus the first function, which was cosine of x, times the derivative of the second function, but the derivative of e to the x is e to the x. And there we go. There's our derivative for this product rule. Now, of course, there's some algebra that we can do here to make this look a little nicer. Both of these terms have an e to the x. We can factor that out. I'm not worried so much with the algebra here. Of course, if you're taking an AP course, then this is a multiple choice question. The multiple choice answers may have the e to the x factored out, so you might have to consider that kind of thing then. But this is kind of the real thing that we do when we're taking the derivative of an exponential function. So let's do another one here real quick. Let's say that we had the function y equals e to the 2x squared plus 3x. Okay, so this one's a little bit different as well. We've got an exponential function, but our exponent here, the 2x squared plus 3x, is actually another function. So we have a composite function that tells me that I need to use the chain rule to differentiate this one. So according to the chain rule, what I do is I take the derivative of the e to the x function, or the e to the something. So I'm going to leave that as e to the 2x squared plus 3x. Taking the derivative of that doesn't change anything, because I'm just taking the e to the something. The derivative of e to the something is e to the whatever that thing was. But the chain rule requires that I multiply that times the derivative of that inside function. So in this case, I would want to multiply that using power rule. The derivative of 2x squared is 4x, and the derivative of 3x is just 3. And so using the chain rule, my e to the of an exponential function, I bring down the exponential function. It doesn't change at all because of the rule for derivatives of exponential functions, and then I multiply that times the derivative of whatever that exponent is. Okay, so again, not too terribly difficult to do, and we'll get some more practice with this in later videos when we're just going through and practicing taking our derivatives. Okay, so there's our exponential functions. That's how those are going to work. Hopefully you'll find those relatively simple to do. They're not too terribly difficult, especially the e to the x function, since it's its own derivative. You just got to look out for those product and chain rule issues and things like that. Okay, so let's move on and talk a little bit about our logarithm functions. This one's a little bit, the proof of it's actually really simple, but the idea of how to get there doesn't seem as straightforward. Might not think of how to do this if you weren't seeing it for the first time. So let's say that we had y equals the natural log of x. Now I'm just gonna work with the natural log function here. I'm not gonna. There are rules that involve logarithms of other bases, something other than e. But we have a change of base formula in pre-calculus that we can use to put anything that we want to into a natural log function. And I highly recommend that you do that because these natural log functions are far more easy to differentiate than the logarithm functions in log base 8 or log base 2 or anything like that. So the first thing that I would always do is use my change of base formula and convert this to a natural log. Okay, and I'm not going to go through that. That's an algebra skill. If you're struggling with that, there's some videos online that you can use to work with how to use the change of base formula. It's relatively simple to do as well. Okay, so like I said, we're not going to have to go back to our limit definition for this one. We can actually do this without the limit definition. What we're going to do instead is we're going to manipulate this algebraically and see if we can figure out how to find the derivative of this without actually doing the limit definition. So what I'm going to do here is I'm going to exponentiate both sides. I'm going to raise both sides of this, make them exponents on e. So I'm going to make it e to the y equals e to the ln of x. Okay, now when I do that, of course, there's not much that I can do with this e to the y, but e to the natural log of x, the e and the natural log are inverse operators, and so they cancel each other out, and so the right side of this, if you remember from pre-calc, simplifies to just x. So basically I've changed this function from y equals the natural log of x to e to the y equals x, and you can probably see why I did this because we just talked about how to differentiate an exponential function, and that's what we're going to use to differentiate this one. Now, one of the things that I haven't really talked about yet that we're going to be talking about in a couple of videos is something called implicit differentiation. I'm going to use a little bit of that here when I differentiate this, and I'll kind of talk a little bit about why this works the way that it does, but I'll get more into this when we do our implicit differentiation. So let's say remember we're trying to find the derivative of y with respect to x. We need to find y prime or dy dx. Okay. So what I'm going to do here when I differentiate the left side of this equation is I'm going to take the derivative of e to the y, and based on our exponential differentiation rule, that's just going to be e to the y. This is the implicit differentiation part. I actually have to treat y like it's a function here. It can't be treated like it's just a variable. And so I have to multiply this times the derivative of y with respect to x, which of course is just y prime. So that's where I'm going to get my y prime from right there. We'll talk again a little bit more about this when we do our implicit differentiation. And then the right side of this, the derivative of x, of course, is just going to be 1. Okay? And now I'm going to solve this for y prime because that was the thing that I actually wanted to find here. And I find that y prime is equal to 1 over e to the y, which doesn't seem like it's helping me very much. I've got a relatively ugly equation now that I have to deal with. But the thing that you have to recognize here is that we already know that e to the y is equal to x. We've already found that. And so I'm going to replace that e to the y right there with x. And so it turns out that the derivative of the natural log function turns out to just be 1 over x. Okay? So there's our rule for that. The derivative of y equals the natural log, the derivative of that is going to be 1 over x. Okay? So there's the proof for it. That shows why it works and what the derivative actually is. Let's actually put this into practice a little bit and see if we can find a couple of derivatives for this as well. So let's say that we had the function, let's do the natural log of, let's say that we've got f of x equals the natural log of 5x squared. Okay? So if we're taking the natural log of 5x squared, using our properties for the derivative for a natural log function, the derivative of this, or f prime of x, is going to be equal to 1 over, again, we're going to have to apply the chain rule here. We've got a function 5x squared inside another function ln, so we've got a chain rule issue. So I'm going to take the derivative of the outside, which is going to be 1 over whatever I'm taking the natural log of, in this case 5x squared, and then I have to multiply that because of the chain rule times the derivative of the inside function, which in this case is 10x. And of course we can simplify that algebraically as well. 10 over 5 gets me 2. And of course I've got an x in the numerator and x squared in the denominator, and so this derivative turns out to just be 2 over x. Okay, so there's our derivative for that one right there using the chain rule. Okay, we also might run into this with some of our other properties. Let's say that we had the function f of x equals maybe something like 3x squared times the natural log of x. Okay, now I have a function times a function. That's a product rule problem, so when I take the derivative of this, I'm going to have to use the product rule. So the derivative here is going to be the derivative of the first function, the derivative of 3x squared using the power rule is 6x, times the second function, which was the natural log of x, plus the first function, which is 3x squared, times the derivative of the natural log function, which is 1 over x. And of course, I could simplify that again and make this 6x times the natural log of x, plus that x cancels with one of those, and so I just get plus 3x. Okay, so there's an example of using the natural log function in the derivative for that using the chain rule, and another one using the natural log function with the product rule. So those are two more rules that we've got to go. We're almost through all of our rules for differentiation. I know this has been a long process. There's a lot of these rules to go through, but we're going to be using these things all year long, so we've got to make sure we've got a really good handle on these. There's a couple of more of them that we're going to do, and then we'll get to some videos that will just kind of practice everything and throw all of it together.